Okay, my name is Steve Prusha. I work at the Jet Propulsion Lab. We're a Caltech lab that does this for a living. I think I have a great job. Welcome to I.O. So I go in the morning and try to find out ways, for example, to explore volcanoes on I.O. This would be a Tuesday, and the Wednesday we do something else. About a year ago, you heard from Brent Sherwood, who talked to you about a facility or capability at JPL called TeamX. TeamX is a concurrent design engine at JPL that develops the conceptual designs associated with these sorts of missions. Our particular job here at JPL is a little bit different than most. So first I want to talk about what we're doing here. Then I want to talk about what my job really is at JPL, which is to put this capability out of business, mainly because if I don't, somebody else will. So my job is to look out 10 years and completely redo TeamX, clean sheet it, and make it obsolete. I don't know exactly how to do that, but at this point I think we've determined pretty well what needs to be done, and that's what I'm going to throw out as a challenge to this group here. So first of all, let's make it clear, we do one of very expensive things. Our missions run about $100 million for the cheap ones, up to about $2.5, $3 billion for the expensive ones. The Mars rovers that everyone knows about still moving around on Mars, somewhere in the middle of that range. But they're all custom jobs. Once we get to the second one, with the exception of the two that we just built here on Mars, we send it out and somebody else takes care of it. So we're doing 3 Sigma designs. We have long design horizons. This is one of the biggest challenges. We will build, develop, or rather design, build, launch, and finally get our science back in sometimes 15 years, 20 years. Voyager launched in 1978, still operational. So we have to build our systems with the sense that they're going to last a long time. We also don't know our environment. In the particular example, we just finished a Titan encounter. We didn't know whether the surface of Titan was liquid or solid. So let's just say there's a lot of uncertainty associated with that. That tends to affect the robustness of the design as well. And as a result of that, we can't test them well, and we're at the edge of physics in a lot of cases. We're on the surface of Titan, we're on the surface of Venus, high radiation environments and so forth. So we've got a tough design job. Next chart. Okay. I want to just revisit one point that Brent had made a year ago and really go down to the last one. We had to move to a concurrent design game because in the mid-90s we were doing one study at about 500, 600K each. We could do about 10 a year. At that point, the breadth of our trade space really exploded. We put a concurrent design capability in place here and reduced that now down to roughly, really the bottom line is the point here. We are now a trade space population game. We can do up to 100 studies now in a single year. We have a decision latency that allows us now to get to one study, a complete mission design, clean sheet, in 1 week. Now we want to put that one out of business. Next. This is the physical configuration. We have roughly 2 teams, figure 20 chairs, roughly corresponding to a subsystem decomposition of a spacecraft or a mission. About 30 people staff it. We run it really fast. We start on a Tuesday morning. We converge by noon on Friday. We run the people for only 3 hours at a time and let them rest and come back. We often have these both running in parallel. Next chart. Now, let's move forward 10 years. And I say it's 10 years. I'd like to say 5 years, but things take at least twice as long as you think. So we're setting this out here. What's going to have to happen in 10 years for us to be competitive in this particular market? And these are the key things here. And the next one are really the key difference makers that I'm going to really throw out to this crowd here. So number one is everything's model-based already, I'd argue. Very little is integrated to the extent that we need to see it that way. All right? What I'm really talking about is integrating the performance side, that is the component models, the functional models, the phenomenological models describing science, our principal product, with the implementation models, cost, risk, schedule. I want to see a design change on the left reflected immediately in this environment with the kind of a cost schedule change on the right. We are nowhere near that at this point. The second one is I want to be able to interrogate the models once they're done. I don't want a CAD model. I don't want just an orbital model, a mission model. I want to understand why these decisions were made. This is perhaps the toughest nut to crack. I need to interrogate that because I'm looking at far enough horizon out. I need to know if power subsystem guy has been using the right assumptions or not. I need to know if this particular designer is using the right, or the designer performance is equitable or not as well. And I need it fully distributed. I need to go outside JPL, private, university, international, and I need it not hub and spoke. I need my sidebars to be done outside of JPL. I need them done immediately in the same time scale that we have going right now. And lastly, I want to talk about the 3 difference makers. Number one is visualization. This is a job I don't know how to do. Soft attributes. I don't need another CAD model. They're great. I never align my parts in the spacecraft and have a problem. I need to know how risk lays over that CAD model. I need to know where cost lays over that CAD model. That's what's important to me right now. I also need these models to be very agile. I need to be able to change them in quick time. And I need perhaps the biggest challenge right now I don't know how to get around is when I'm trading designs or hardware, easy. When I'm getting models from vendors and trading them back and forth, I'm actually dealing with intellectual property. This has become one of the biggest problems today in the model-based design paradigm. Thank you.